Today, we talk a little bit about what exactly is process mapping and the purpose of doing such kind of mapping. We actually identify what takes place in value adding and wasteful activities. We also look at the design of simpler and more effective systems. In addition, we try to understand the different players, tasks, and activities in the process. Value stream mapping or process mapping includes all elements that occur to a given product from its inception as a raw material, from delivery to the customer. These elements are both value as well as non-value added. When we talk about what is meant by value added element and what is non-value added element, we need to look at a term called waste. Let us define waste in this particular context. Any activity that uses resources but does not add value to the product or service can be considered as waste. In Toyota production system, there are 7 commonly accepted lean kind of waste. You may call it lean production within the Toyota production system. There are 7 kinds or types of waste. Now, what is meant by value added? Value added element actually adds real value to the worth of the product, which is what the customer pays for. Non-value added activities have to occur in order to get the work done. Now, let us look at the 8 types of waste. These form the core of lean philosophy in both service as well as production. The first is transportation. Moving items around the operation or together with the double and triple handling of work in process does not add value. Layout changes, for example, which bring processes closer together, can be made to reduce this kind of transportation waste. Improvements in transport methods can be done, and workplace organization can all reduce this kind of waste. The second is the inventory. Any more than the minimum amount required to get the job done is actually considered waste in the inventory context. All inventory should become a target for elimination. However, it is only by tackling the causes of inventory that it can be reduced. Therefore, this is one area, inventory, where a lot of waste can be reduced. The third is the motion. Any motion of man that does not add value. For example, an operator may look busy, but sometimes no value is being added by the work. Therefore, simplification of such work is a rich source of reduction in the waste of motion. The fourth kind of waste is waiting time. It could be for parts or people or machines. Now, equipment efficiency and labor efficiency are 2 popular measures which are widely used to measure this kind of waiting time. Now, less obvious, of course, is the amount of waiting time of items, which are usually disguised by operators who are kept busy producing work in progress which is not needed at that particular time. Therefore, the waiting time is also another type of waste. We have something called overproduction, producing too much or producing too soon. This is considered as the worst kind of waste because it hides or generates all others, especially the inventory waste. Producing more than what is immediately needed by the next process in the operation is considered, therefore, to be the greatest source of waste according to Toyota. We also have processing waste, overprocessing, where you look at the process itself could be a source of waste. Some operations may only exist because of poor component design or poor maintenance, and so could be eliminated. Then we come to the next waste, which is the defects waste. Any repair or rework or spoilage is considered to be a waste. Now this is a quality waste, which is often very significant in operations. The total costs of quality are much greater than has traditionally been considered, and it is therefore more important to attack the causes of such costs. These form the 7 commonly accepted lean waste in Toyota production system. Now, let us look at the categories of waste which we have discussed, which are the value-added activities and the non-value added activities. These two are considered to be the categories of waste. Now, anything that the customer is willing to pay for can be considered as value-added activity. The action must meet all 3 of the following criteria. The customer is willing to pay, it must be done right the first time, and the action must somehow change the product or service in some manner. Then only you consider it to be a value-added activity. Now, please note that supply chain considers all activities in the process, whereas the value stream takes only those areas, departments or parts of firms which provide value to the end product or service. The other kind of activity is non-value added activities, which is what it costs, that costs money but that does not add value to the need, or that is perceived as waste. Something the customer is not willing to pay for example, waiting time, stacking intermediate products, and double handling. These activities actually do not add any value to that particular action. Now, we'll also look at something called necessary non-value added activities. Now, these are activities which do not add value but which are essential to ensure that the value added activities fulfill the need. For example, walking long distances to pick up parts, or unpacking deliveries and transferring. For these, a tool from one hand to another, this activity also is considered to be a non-valid activity, necessary, non-value added activity. Creating a new layout or arranging for suppliers to deliver unpacked goods. Such changes in necessary non-value activities may not be possible immediately, but they are actually required to get to the value-added activity. Now, we have discussed so far what is waste, what are the different types of waste, and what are the categories of waste. Let us look at the process flow mapping symbols. These are the process flow mapping symbols followed internationally. These are only a few, but there are many more also. But these are very commonly followed mapping symbols. Operation, represented by O. You could remember the first letter of operation as O, and the symbol is the same as the first letter. So it indicates a main step in a process, method, or procedure where a change in the actual state occurs. We will also discuss more examples related to this. Store, a controlled delay in the process where material is received into and issued from a store, or a file or an item is retained for reference purposes. Imagine this inverted triangle to be a storing place. For example, when you throw a few pebbles, this kind of symbol actually stores the pebbles. So you could imagine this as a store. The next one is a transport, the movement between parts of the process. Now, if you tilt the first letter of the word T by 90 degrees to your right, it forms actually a T. You can observe this as a horizontal T. Therefore, you can remember this symbol as transport. Next is delay. The first letter of D, which is D in the delay, is actually represented by the symbol itself, which is an uncontrolled delay in the process. Next we come to inspection, which indicates an inspection of quality or a check for a particular quantity. This is shown by a particular rectangle. These are the process flow mapping symbols. Now, we will take an example from our course itself to look at a person's shopping for silk in Shanghai and analyze the whole process of this shopping activity using these mapping symbols. The person enters the shop, which is actually a movement, therefore considered to be a transport. Then you have the activity which is negotiating with the assistant. This is actually an operation because it is neither a store nor a delay nor transport nor inspection. It is actually an operation. Then a movement by the person to locate the category desk is represented by the horizontal T, which is transport. Then you find the assistant to look at a particular product. Again, it is an operation. Then you want to select the product. You actually do inspection of the quality of the product, which is represented by a rectangle. Once you select the product, the next operation is to write the receipt. From here, you take the receipt to the cashier, which is a transport, and you wait in the queue. The waiting is a delay, therefore it is represented by the letter D. When you actually pay for the product, it is an operation. Then you take the paid receipt back to the assistant, which is a movement represented by T. And when you wait in the queue, which is represented by D, then you get to pick up your product, which is an operation. And while you exit the shop, it is a transport movement. Now, you can put ones and twos and find in the whole process the number of T's, the number of O's, the number of inspections, the number of delays in the entire process. By putting a 1 here, you are trying to understand how many T's are coming up in the process. By particularly targeting those T's, you can reduce any one of those or more of those T's. So you have 1, 2, 3, 4 and 5. So you have got 5 T's. By planning properly, you could possibly reduce the whole shopping experience by a particular time and by reducing these particular T's. The number of operations, similarly, you have 1, 2, 3, 4 and 5 operations. Similarly, you have 1 inspection and you have got 2 delays. Maybe it is possible to reduce the waiting for the second time. Maybe it is possible to reduce 2 kinds of operations in this process. So we need to look at this process innovatively and come at an experience that gives the shopper more delight. If we try to reduce the shopping time and enhance the experience, you can look at the entering shop activity, which is represented by T's, the browsing activity, then you find the assistant to ask for advice. You are actually inspecting for quality right here. Then you pick up the product, which is an operation. You take it to the particular person for paying the cash or by card. Then you wait in the queue. Then you pay for the product. Then you exit the shop. The number of T's have been reduced by 1. You have got 4 T's. And in fact, the delay has been reduced again, and you have 1 delay. The processes again has been reduced to only 2, and the inspection remains the same. So the whole activity of shopping can be reduced by mapping it through this kind of process and analyzing it. Now, after this example, let us look at the 4 process states. These 4 process states are what people say it is. You need to understand what they perceive it to be, what it actually is, and what it should be. This can be represented as something called a process redesign sheet. You write the process and you write the first step here. And to your left, you have got 5 terms beginning with means, person, sequence, place, and purpose. For each of these terms, you have got different kinds of questions. What is achieved? Is it necessary? What else could be achieved? What else should be done? Should you include it in the new process? If yes, then what is the location? Do you need to reorder the sequence? If yes, by who? And by what means? Is it going to be internal or external? Then you have your notes and an approval by your manager. So this is actually a process redesign sheet. Now, when the earlier shopping activity process is actually mapped and then these questions are answered, then actually you get to a better process. Now we conclude the first part of the process. In the next few sheets, we will look at what exactly is meant by SMED, which stands for Single Minute Exchange of Dies, which is DIES, SMED. The name SMED comes from the goal of reducing changeover times to the single digits, which is less than 10 minutes. For many technologies, increasing process flexibility, means of reducing setup times are very crucial. These are defined as the time taken to change over the process from one activity to the next. This is called the changeover time. Therefore, changeover time is defined as the time taken to change over the process from one activity to the next. The setup time reduction is also called by SMED because this was the objective in some manufacturing operations. How to achieve setup reduction? There are 2 approaches. The first approach: compare the time it takes you to change the tire, for example, on your car, with the time taken by a Formula 1 team. Changeover times that improve by a factor of 20 may be hard to imagine, but consider a simple example of changing a tire. For many people, changing a single tire can easily take 15 minutes. But for a NASCAR pit crew, changing 4 tires takes less than 15 seconds. Imagine, less than 15 seconds. Now, many techniques used by NASCAR pit crews are also used in SMED. These techniques used by NASCAR pit crews, they are performing as many steps as possible actually before the pit stop begins, using a coordinated team to perform multiple steps in parallel, creating a standardized and highly optimized process. In addition, the setup time or setup reduction can be achieved by a variety of methods, such as cutting out time taken to search for tools and equipment, or the preparation of tasks which delay changeovers, and the constant practice of setup routines. This forms the first approach. The second and common approach to setup time reduction is to convert work which was previously performed while the machine was stopped to work that is performed while the machine is running. So the work which was previously performed while the machine was stopped is called internal work, and the work that is performed while the machine is running is called external work. The essence of the SMED system is to convert as many changeover steps as possible to external, which is work performed while the equipment is running, not when it is stopped. The essence also includes simplification and streamlining of the remaining steps. There are again different methods of achieving the transfer of internal setup work to external setup work. As we have defined the setup or changeover time as the time taken to change over the process from one activity to the next, we can look at the big idea of SMED. The changeover times can be dramatically reduced, in many cases to single digits, which is less than 10 minutes. Before SMED, all changeover elements are performed while the equipment is stopped. These are termed as internal elements. We need to separate these elements into internal elements and external elements. And after converting such elements, we need to review the remaining internal elements and ask what it would take to make them external. And then try to streamline elements. This shortens both changeover time as well as the external time. Now, SMED was actually developed by Shigeo Shingo, a Japanese industrial engineer who was extraordinarily successful in helping companies dramatically reduce their changeover times. His pioneering work led to documented reductions in changeover times which averaged 94%. Example, from 90 minutes to less than 5 minutes across a wide range of companies. Therefore, the objectives of SMED is to eliminate the waste that result from uncontrolled processes, increasing inventories and lead times, to gain control on equipment, material and inventory, to apply techniques to eliminate erosion of improvement, and to standardize improvements for maintenance of critical setup parameters. Therefore, a successful single-minute exchange of dies program will have the following benefits: reduction in changeover and setup time, lowered manufacturing cost because of less equipment downtime, smaller lot sizes because of more frequent product changes, improved responsiveness to customer demand, lower inventory levels, and smoother startups. Now, the easy way to remember the single minute exchange of dies, SMED, is also by saying stop machine and empty the dirt. Stop machine and empty dirt. SMED. Voila. So you have finished or concluded the first part of our series in operations. Thank you very much for your patience. Bye-bye, and I shall see you soon in the next slide presentation.